Surname's nearly as good as Alex's name. Although I run a brewery in West Wales, I also study a thing called Transcendent Form, which basically is a multi-dimensional thing of form and structure. Take it back to Plato and people like that. And but I'd like you just to listen to 60 seconds of a piece of audio. And in there, just see if you can hear any form or structure. Something that's been brought from a transcendent domain via audio to your sensory perception. Now, I work on this transcendent form from two aspects. One is through art and one for engineering. And that sound has never had any interaction with a human being. It's never seen a synthesizer. And it's actually, I've brought, because we run a brewery, I've bought a super piece of analog hardware here to try and demonstrate the principle. It's called a glass. And a glass is a structure, and when you can just tap a structure like that, you can hear a sound. Now what I do with this transcendent form is bring lots of different structures into computer memory and then generate them with sound. Basically because I want to study these very complex forms, and I need some help in looking at them as complex and in several dimensions. So I'm working on the principle that visual imagery helps, and I'm actually trying to do like synesthesia as well, where I'm generating sound from the vision so I can look what I'm hearing and hear what I'm looking at. Now, to do that, the big thing in memory is the sort of structure of a glass, big crystal. And what we do is we can draw a little domain around a piece of the glass and say, what does that sound like? And then we can draw another one. And what we can do then is to draw lots and lots of little ones and define a trajectory as a timeline. So then we can listen to that timeline and say, what does that glass sound like going from there to there? And that's now been termed GTAG. And it's called Graphic Trajectory Audio Generation. I've got a close that down. This is a presentation I gave in London about 18 months ago at the gallery for the Parallax Art Fair. And it basically describes how this GTAG works, and it starts off with a basically plain MPEG. Should we plug the TV? Or what can plain MPEG? Like plain API.
So if I go get it and play it, thanks.
HD, MKV.
Did you say yours was good?
Yeah. It's my laptop.
Yeah. Anyway, what it is this GTAG, basically, when we have the glass, we define a little area, and we convert all the little pixels to frequencies in that structure. And in itself, that will create sound, but not very interesting sound. Because what we want to do is to take this sort of geometry and find structure of the thing in there. So if you had, say, a piece of graphics and it had 10 blue pixels in there and 3 green, you'd have a piece of sound, but no matter how you juggled all those pixels up, you'd end up with the same sound. So what we have to do with GTAG is to try and include the geometry into the audio, and you can do that by saying things like, if you have a red pixel next to you on your left, you can change the harmonics and things like that. So you can develop lots and lots of rules to start generating the sound. So you can take a 2, 3, 4, 5-dimensional piece of graphics, create a trajectory through it, and then generate sound. Now that's my work, to try and do that with some efficiency, so I can look at these complex objects and try and work out what I'm trying to do with them.
What do you mean by transcendence?
Transcendent, it means, basically philosophically, it means something that's beyond time and space. This is where the Greeks came from, with Plato and people like that. That we experience only small proportions of this domain as sort of shadows. That's the basis of Plato's philosophy on the forms. Me, as a mathematician, I come from a different angle. I can follow some of what he says, but from my thinking of transcendent is that I can actually derive from that things like dimensionality and number, and I can extract forms from there. It's a place where big isn't a word you can use, because transcendent just means more than you could ever think of. But I can actually go in there with a computer, drag out forms, display them as things as bitmaps or 3D volumes, and also generate it into sound.
What was this, the object that we heard? Was it this one?
No, it's a piece of graphics. I don't know where that piece of graphics is anymore. It's a form easy.
Yeah, I'll sketch that away.
You want the sound as well?
Yeah.
We have to find the...
I'll get sound from over
Yeah, the actual sound was just a little example. I did that because a lot of people said to me that's come out of synthesizer. It hasn't. People have been involved in it. It hasn't. They must have been involved in it because it has like a compositional structure. I can hear almost music, but it's what fascinated me all the time. That you can create sounds like that, and it's just like tapping a glass. And if you tapped a glass, and that sort of sound came out of it, you'd think that's a piece of spooky glass, wouldn't you? And okay.
The third one?
So what I'm doing in this presentation is we start off with a two-dimensional aspect and introduce you to GTAG, where it starts off, you'll see some coloured little bits of graphics moving through a zone, and as it moves through, it will create sound. And we start with a very simple square, and then a square within a square, something a little bit more complex, and more complex still. And we'll go through different scenarios where we'll move on to a larger piece of graphics, and then one where the zone can actually move through the graphics. And I'll pause it at that point, carry on. Is it easy to use a pause?
Yes.
So, alright, yeah, I can just play and pause, yeah?
Yes or no?
Okay.
No? It's pain.
Right, that's 2D. demonstrating the idea of sound. As it goes through that sound zone, so that's the graphics moving through. The light of it is the actual zone generation. And it doesn't have to, you can actually have the graphics static and move. And what you need to point out is the sound there is generated from those graphics. Doesn't have to slide, you can tap.
So is it each colour a different pitch or something like that?
Yeah, it's a different frequency. Just pause it there.
That sounds like bagpipes.
What I did in the exhibition as well was I tried to use a three-sensory approach where we took the graphics, can't just see very well on the right there, we rendered that to a piece of slate, the actual image, so people could have headphones on, they could hear this sound. The sound's generated purely from the geometry of that, and then run the fingers down as well. So they were actually sensing things in three units there. And the thing I picked up there was one chap came up and he said, well, it's not a fossil, and because it was on slate. And I said, well, why do you think it couldn't be a fossil? And he said, well, it's not natural, because natural things don't make patterns like that. And it's obviously not done by a caveman, because cavemen wouldn't actually do these sort of geometric types of graphics. So it must have been you or someone else that did it. And I said, no, there's a third alternative now. There's, what I work with Transcendent form is it brings structure to us, and you look at that structure and you think it looks familiar, but this basically stems from number theory. So I'll just finish it off. Everything you can hear in there is just, it's quite a simple thing, but I should have brought the piece of slate. No. I don't know you were stuck. There we go. There.
It says working. We have to press it here, I think.
Alright, then.
No, okay.
So people were actually listening and they were watching that slide through those bits of geometry and actually touching the slate as well. Okay. So we can actually go into 3D as well. So that was just examples of audio generations through 3D. Now 3D's got two demonstrations here. One, you can see the sensing zone going over the 3D. So we've gone from pixels to voxels, 3D things. And then the second demonstration is of 100 billion voxels, which have been broken down so you can see inside. And as the film progresses, you see are you familiar with voxels, the 3D pixels? Most of them will shrink to zero, leaving the bottom layer visible. And then that layer will separate into 5 colours, so you can see the interacting complexity of everything. And all the 3D sound as well, you'll notice is a lot richer, which you'd expect, because you go from a square number of pixels to then to a cube. So there's the zone moving through that. A more complex 3D image, but you're not seeing the pixels. It's hard to display, but the sensing zone is somewhere in the middle there. Where it starts, pixels start, the voxels start going to zero to leave the bottom there. And if you're interested, you'll be able to see a much higher resolution images on there.
These transcendental forms, are they idealized forms in that platonic sense?
I don't know. I just know how to get at them on the computer. Now, here's a 4D example. I'll just stop there. The way I've tried to work with 4D is to imagine a line breaking up into little points, and then to imagine a plane breaking up into lines, and then to move further to imagine a volume which will break into planes, and then to try and make the next step to imagine a four-dimensional object breaking into volumes. So what this does, it starts with a four-dimensional block brought into 3 space, and then extracts itself into 3 spaces, a number of cubes. I hope that makes some sense. And the sound is 4D there, and I just point out that when you're working with GTAG, when you're moving a sensing zone over discrete objects like pixels, if you don't blend them, it'll click as you switch from one pixel to another. So you do blend the sound in as it moves through different pixels. In this example, I switched that off so you can hear it clicking between the zones, the volumes in the 4D. So there was a centre volume there, and then that is breaking up. You think of it as a point in space, and then all these things come out of there. Probably the first time you'll have heard a four-dimensional sound. Okay, we include dance now because you've seen the trajectories there. They've been produced by the computer moving the sensing zones through the graphics and the volumes. A little while ago I met up with a chap called Thomas Freundlich. He's one of Finland's good contemporary dancers, and although his training is with through the Swedish ballet, the Finnish ballet, he's also what I call tech savvy, and he's not scared of people like me that come along with computers and mathematics, because he's done 2 operas now with industrial robots, and so he can program robots, he can talk mathematics, he can dance ballet, he can dance hip-hop, rock, and so we met up in Holland at a company called Xsense, who make the motion capture suits. And they consist of about 18 or 20 accelerometers and flux gate compasses that give a really good description of body movement. So what we did there was to spend a couple of days and we recorded different types of dance styles, going through ballet, through all sorts of things. And I recorded them, well, we recorded them. And with the data, I started using his movements to generate the sounds through the it's called the sound space, we call it. And so the first one you'll see, he'll control the volume with his left hand at the presentation. Then his right hand will be tracked, a bit like the Kinect, but with a lot more detail. And you'll see it moving through the graphics to produce a sound. And just do that one, and then you get an idea of what goes on there. You'll also see the avatar above it. That was a simple example of that. You can go into more ballet style, and again the audio then is generated from that graphic on the right hand side, and it's tracking his right hand in the XYZ coordinates. Thomas is quite a creative chap as well, and he wasn't satisfied with that, that he could make sound. What he had to do, he had to come back and say, what happens if we come back with some MIDI recognition software that will recognise the music, and then reconvert that sound that I've just created back into music which we can score, that we can then give that score to an orchestra to play from what I've actually danced. And so what we did in the next couple of examples is that we ran MIDI software through the audio we generated by dancing, and then that was, it's quite easy with the MIDI software just to create a grand piano. So we converted his dance into a grand piano, and then he arranged it, but not adding things, but just using the bits he had there. The piano is not brilliant, but it goes to give an idea what goes on. So you might ask the question, now why bother to do all this? That somebody takes transcendent form, brings it into our 3-space inside a computer, dancers dance in it, and why don't you just get a guy in one of these suits and hook him up to the MIDI ports and things like that? It's because we're working on a new type of instrument where the whole body of the dancer becomes instrument. That if you're playing something like a cello, you're fairly restricted. You're probably doing that. And if you pick the cello up and ran around the room, it really wouldn't make much difference to the performance. So we're splitting it up into 3 parts now, where you have something like a traditional performance, where you have what's called a composer, but in this sense, he's a GTAG composer. He plays with the graphic, and he creates trajectories, and likes the sounds that he gets here and there, hooks them all together in the timeline, and works with a choreographer, who then works with the dancer to actually have the GTAG going through the composer's trajectory, and then the dancer interprets, adds little bits to that trajectory to put his own little interpretation on. So we're trying to get the thing together between a composer, a choreographer, a dancer and an audience, where the audience can see the actual dancer working his way through this sort of, and it's 3-dimensional crystals as well. It's not, if VR helmets were any more advanced than now, we could probably sit down and put a VR helmet on and experience a dancer going through this crystal, or 2 dancers, or 5 like that. So that's the artistic side up till fairly recently. And Tim actually triggered me into doing something which I hadn't planned for a little while. He said, can you actually get something interactive for the show? Which I tried very hard to do with the Kinect box. The suit that you saw Thomas wearing there, it cost about 100,000 or something, it's just full of all, but the radio connected. So your dancer has full 3D movement in a big volume. So you can do anything he wants, jump up and down, spin round. Kinect's a bit different, but I was hoping to get it for the weekend. I'll try and get something down in a week. The problem is the G-tag, you don't stream audio. You've actually got to compute your whole little computing zone real time. And if you're trying to do that at 44 kilohertz, doing a lot of computations, you start running into problems. I just got some new hardware in from NVIDIA, you know, the GPUs. It's about 1,000 on the card here, and it's struggling a bit, but we might be able to do something. So that's the artistic side. There's another side to it, which is engineering, which it probably these are part of transcendent structures that are quite complicated, and my engineering background in this is to do with nanotechnology. What we're trying to do as well is to create these forms at very small scales onto things like chips. And the idea of that is that what's happening at the moment is people are finding when they create these very complex forms on chips, they can actually interact with light as they could with electricity. So I'm trying to take that a lot further. That my aim is to interact with gravity on that. The reasoning is that when you get down at very small levels, you know, down to nanometers and hopefully picometers, form becomes the thing that means everything. So shapes, geometries are the things that define how things will interact. And hopefully I'm going to, in August I'm going to San Diego, and I'm putting the engineer's hat on there, taking the artist's hat off. And I'm giving a presentation at a nanotechnology and photonics conference there. It's 4,500 delegates. I'm a little reluctant to put a dancer up there saying this is how science should work. but that's the main objective of the engineering side, to start getting some of these forms onto materials at very, very small scales and seeing how they interact with nature. So, to me it's becoming clear what a galactic class star drive is going to look like. You might have some questions.
Well, thanks first of all.
Wow.
So transcendent numbers are a type of mathematical number. Are they like irrational numbers?
No, this isn't transcendent numbers. This is transcendent form. Right. Which is something. It's a fuzzy grey image somewhere. And out of that, what you do with the computer, you drag these forms. Now, I've learned how to do it, to drag them down into a computer memory as geometric images. They're controlled by natural numbers, which are the 1, 2, 3, 4, 5. Prime numbers have a major important role in there, but your concepts start having to, if you thought quantum mechanics is screwy, this gets even worse, because you have to start imagining things like, normally you would think a number 7 is not divisible by anything except 1 by itself. That's why it's a prime number. But primeness and numbers, it seems, are a bit more, there are things which those are containing. So you can have something like a red 7 that's divisible by a blue 5 has a whole number. So this is where all these patterns come from, where natural numbers are actually just the first thing we've come across. Transcendent form contains a whole new concept of numbers. Which
so is this something you've discovered yourself? Or?
Yeah.
But are other people working with transcendent form?
Not much, really. There's been a few historically. I see the last two people to work on this were Pythagoras and Euclid. Those are the last two. Pythagoras, with the work in his with prime numbers and in some geometry, and Euclid, he was really one of the first people to start thinking about an algorithm where he could actually do a series of steps with numbers go round and round and round and come out with an answer. Knowing what I know now, I could have gone back and sat with Euclid. We could have drawn squares in the sand and used those as computer memory and used pebbles as numbers. And I could have taught him how to make very simple patterns, but why these haven't come about is because they only start becoming obvious when you start getting up into the hundreds of megs and the gigabytes, the terabytes. It's like a mechanism that stops you going into this domain until you've got the right technology. So it's called a sentinel. It's very... I have a problem at the moment because I don't have the right language. Apart from trying to show people pictures and say, well, I've got that from somewhere. It's fairly complex. You've got to decide whether it's just a piece of junk and nature playing tricks on you, or whether you can see in it. Somebody wrote back to me, and they did describe that as, they said it was cipher-like, and it interprets the viewer in to interpret the meaning. It invites the viewer in. And that's how I see it. I see function in there, and I want to get these onto materials and put a battery on them and power them up and see what happens.
In a way, and I'm just, obviously, it's not the same thing, I recognise that. It's reminiscent of fractals. There's something in there which is like a...
Yeah, fractals, I've got two things on fractals. Fractals, one, they deal with digits, real numbers. So you get 1 point something. This whole theory excludes anything to do with things like real numbers, functions, mappings, everything you do with mathematics, differential equations, things like that. You can't do it with this. You can only use whole numbers, and I think that's the reason for that is because any computation you make with whole numbers, they're exact. Now this thing, when you work, it's called the transcode algorithm, and when you work with the algorithm, you soon realise you work with perfection. Only because you use natural numbers. 3 from 2 is always 1. There's not one bit or so, and it's because of that perfection you get the.
That's what the question I was asking is. Plato's maths was of idealised shapes and forms, and I think you're reaching into the same world, maybe on a different scale. Hence, the idealised regular forms you're getting here sound harmonious.
Yeah.
If they were not regular forms, they would sound discordant.
Yes.
So the harmony is in the algorithm, and as you bring it in and turn it into sound, it sounds harmonious because of that.
Well, the harmony is actually in the form that we get.
Or in the form that we bring
and this is the other way I want to go around it. Why are we so fascinated with some sounds? Why do we like classical music and things like that now? Some of these, when I've been working with them, one comes to mind, like the New World Symphony. Just 2 or 3 seconds came into this, and I sat and listened to it and thought, wow, is that what we're all working at?
The musical harmony, is that because you selected the scales which to map those onto?
I select the scales because at the moment I'm working with very, very simple pixel images. The way the theory works is that the higher the prime numbers go, the bigger the patterns get, the detail. So I've been working with fairly low ones because it's a memory requirement. But as you go higher up in the prime numbers, you get bigger and bigger shapes, which, what I'm trying to do with those now is to use every pixel as a frequency and not use anything from music. So they all create all the harmonics and things like that. So
I'd love to read a book about this whole theory.
I'd like to write one, but it's a frustrating point in research when, I've talked to other mathematicians and they've looked, when I mentioned the red-blue 2 and a triangular 7, they tend to look at you with a... And they say, what do you do for your main living? I say, I run a brewery. that does tiny.
Alex.
Very, very interesting. I just want to make it clear. So you have these patterns and you scan them, and you use a different word, I can't remember. With this rectangle that...
the rectangle passes over the pixel image.
Over the pixel image, and then you map this into scales, I suppose, because...
I do at the moment, I don't have to, I could just map.
Okay.
Each pixel represents a frequency, and that's all there is there. So
but it's a frequency, but it's.
I define the frequency at the moment. I use a musical scale.
You use musical scales because I had triads, major triads, minor triads all the time. So so you filter. It's like filtering the.
Have we got time?
Yeah, sure. I think it starts at about 1:30.
I've got 4 short examples on. How do I get back up there? This is just a bit different because I don't actually show the graphics to generate it from, but I use all the harmonics from the graphics to generate different patterns. And I use 4 different scales for the 4 different. At the end, sorry. All right. Right. That's an album I've got at the moment. So these are generated from GTAC, but they actually use. NVIDIA cooling this. So that, I've got a duck. So, let's go back up.
Just go with the window that's behind.
Good idea.
Oh, just the corner.
All right.
Don't touch it.
Just go to that directory. Okay. Now, to read a PDF this way. Yeah. Now these are the production notes to make those sounds. Basically there were four sounds there, and these are the typical graphics that we're using. They're not very clear there. But on the first one, these were the prime numbers that we used. 3 of 13, whatever that. I used, on the first one, a minor scale, and you could probably hear the minor. And the actual lines, there were 7 octaves in the lines, and as they bent in and out, those are the different harmonics coming. The second one, the vertical had 7 octaves on there, but it had like things that were spinning. Now those are the actual amplitudes of the notes, and the bits in between with the actual harmonics. I used an ultra Locrian scale there. Gives it a bit of a classical theme to it. Third one, where you had little things coming in and out and rotating, the actual amplitude of it was coming into the pattern, and as the little circles twisted around, and those are the harmonics. And then the last one, where it's more of a free form, that was done with an Egyptian pentatonic scale. So you can, at this level, when the graphics are very simple, you can plug scale into the mapping from your pixels to sound. And those are the speeds that the trajectory went through that in pixels per second.
Well, thanks very much, Stefan. Hopefully we can get some of these going
Yeah, they'll be on there much
interactively this week.